There are times when you're evaluating double integrals or iterated integrals that you want to change the order of integration just because it makes it easier to do the integral. If you're dealing with a region that's rectangular, then it's really easy to do. If you're integrating x from 1 to 2 and y from 3 to 4 or whatever, I mean, you're talking 1, 2. So, if I'm integrating over that square up there, it may be inconvenient to integrate with respect to x first and you want to switch to doing it with y first. Well, this really is easy to switch the order when it's a rectangle. I can just take these things and turn it around. Right, so instead of dx dy, I now have dy dx. And the way I think of what the limits are telling me, they start on the outside. Here I've got y on the outside, and so y is going from 3 to 4. And for each value of y in between, the x is running from 1 to 2. Right? And it doesn't matter which y I choose in between, this one down here or there, any one of those, the x value starts at 1 and ends at 2. Okay? When I'm looking at this setup, I'm saying, okay, for each value of x between 1 and 2, what's the y value doing? Well, the y value is supposedly running from 3 to 4. So no matter which x down here you choose, you're going to start with your y value at 3 and go all the way up to the y value at 4. So you're describing a rectangle there. Every single vertical line is the same. The bottom is at 3, the top is at 4. Every single horizontal line is the same. The left is at 1, the right is at 2. So no matter how you do it, which order you do, there's nothing really that changes in the limits. It's just which ones are you writing first. Okay, and you may see where, on something like this, you may really want to integrate this with respect to y first because you don't have to do integration by parts, and maybe something nice will happen. I don't know, you probably still have to do parts on x, but whatever. The trick comes in when the region you're integrating over is not a rectangle. So, for instance, here's an example where, let's say 0 to 2, and the integral from x squared to 4. And the function really doesn't matter from the point of view of reversing the order. So I'll just throw any old function in here. So this is dy dx. I know it's a dy dx because, again, the outside integral has got to be constants, and the inside integral, the limits here of integration might be functions of the outside variable. So here I had an x squared, so the outside variable had to be x. Right? So in order to reverse this, I want to rewrite this as an integral, same function, but dx dy rather than dy dx. And so I want the y's on the outside. I can't just take the 4 and the x squared and stick them out here, because then I don't have numbers. I have a function out here. This is a number. When you calculate this, this comes out to be like 7 or 15 or some fixed number. And if you end up with a variable on the outside integrals, then it's not going to be a number. It's going to be a function. So what I need to do is I need to actually look at what region is being described here. Okay. So what I see is that for every value of x, I'm looking at the outside variable first. So for every value of x between 0 and 2, something is happening here. Okay, so I'm gonna actually redraw these a little bit nicer. There we go. So I'm gonna call 2 that far, I guess. So between 0 and 2, something's happening. For every value of x, something's happening. Well, the y value is starting at x squared. So if I look at the graph y equals x squared, And I'm saying for each value of x in here, that value of y is my lowest y value I'm interested in. The highest y value I'm interested in is 4. And actually, I just happen to notice that if you plug a 2 in, you're going to get 4. So for each value of x, these are the y values you're interested in. Pick a value of x over here. These are the y values that I'm interested in. The upper value is always 4, no matter which x I choose. The lower value depends on where you are and what value of x you are, so that you pick the y value on that curve. Okay. So the region that I'm describing then, all these vertical lines are describing this region here that's above the parabola, below the line y equals 4, and apparently in the first quadrant because I'm taking just positive x values here. Okay. So now I want to say, okay, describe that same region, but do it from the point of view of y on the outside. So I need to first of all establish what's the lowest value of y I'm interested in, and what's the highest value of y I'm interested in. Absolute, just biggest to lowest, right? The lowest value I see is right down there at y equals 0. The highest value of y I see that I'm interested in is up there at y equals 4. Okay. Now, for each value of y in between, I'm only drawing one, but I want to think about being able to slide this point up and down and see what happens. Well, it seems that down here, the lowest y value is 0, the lowest x value is 0, the highest x value is whatever it is on that curve. Up here, the lowest x value is 0, the highest x value is, well, whatever it is on that curve. So it looks like the x values are bounded between 0 and whatever the x value is on this curve. That's going to depend on what y is. Well, that curve is y equals x squared. If we solve for x, we've got x equals the square root of y, and it's the positive square root of y because I'm over in the first quadrant. That's going to be my right endpoint here. So this is the square root of y. Right? Outside integral is in just numbers. The limits on the inside integral are either numbers or functions of the outside variable. So there's a 0 here and a square root of y, and that's okay because y is the outside variable. Okay. So that's the this integral should give us the same value as that one, but I've reversed the order of integration. Okay. Let's do this. How much time do I have? Let's evaluate this integral. So evaluate this integral here. The integral from 0 to 1. The integral from 3y to 3 of e to the x squared dx dy. Okay. This is kind of an interesting one because e to the x squared, there isn't a nice antiderivative. It has an antiderivative, but it's not written in terms of anything, any of the functions that we know. So it's really, really inconvenient to try to integrate with respect to x first. Okay. So let's change the order so we can integrate with respect to y first. So I want to set this up as an integral, same function, but dy dx. Okay. So I got to establish what region I'm looking at here. So I'm looking at this thing saying, well, x is going between 0 and 1. No, I'm backwards. The outside integral is y here, isn't it? So y is going between 0 and 1. Okay. So let's get rid of that. And then for each value of y in between, I'm starting off at an x value of 3y and ending at 3. So there must be a line in here of x equals 3y. And in particular, I didn't draw it quite right because now that I see what that looks like, because when y is equal to 1, x is 3, and that's my biggest So it looks like I should draw more like this. So I'm starting here. I'm going over to 3. Notice that when y is all the way up at 1, y is all the way up at 1, this is going from 3 to 3. That is up at 1 here, you've got this really short, just a point that you're going. When y is at 0, you're starting at 0 and you're going to 3. So down here, you're going from 0 all the way out to 3. Right? So the region that's being described by all these horizontal lines is that that triangle. Okay? So switching now to having my x's first, I'm looking at this saying, what's the minimum value of x I want? What's the maximum value of x I want? Well, it looks like the minimum value is 0 and the maximum value is 3. For each x in between, what's going on? Well, for this x, you start at 0 and you end up whatever that is. For this x, you start at 0 and you end up here, 0 to there. So it looks like x is always bounded by 0 on the bottom. And then it's bounded by the y value on that line. Well, I have that line described as x as a function of y. Let's turn it around and so divide both sides by 3. So y is 1/3 x. Now, I might be able to actually do this integral because I'm integrating with respect to y first, and this is just a constant with respect to y. So yeah, that would just be y times e to the x squared, evaluated between 0 and 1/3 x, plug stuff in here. I've got 1/3 x e to the x squared minus 0. And you're still integrating from 0 to 3 dx. Well, now this is an easier one to do because I've got this x in here. Because I can do a u substitution with u equal x squared. Du is 2x dx. So I'm looking at an integral of 1/3 e to the u du divided by 2. The x dx turns into du divided by 2. Okay. And I'm choosing not to worry about the limits here. So that's equal to this, equal to this. Here we go. So I'm going to have 1/6 e to the x squared evaluated between 0 and 3. So I've got 1/6 times e to the 9 minus e to the 0, which is 1/6 e to the 9 minus 1. Okay. It just so happened that the region kind of helped us out in this integral. That is, once you plugged in that limit, you got an x to be the du to go with the e to the x squared there. Anyway, there are times when this is a convenient thing to be able to do, to swap the order. One last time, swapping the order has nothing to do with the function. It has everything to do with the region. So you've got to draw the region, figure out what it looks like, and then start from scratch and saying, okay, if I got my x on the outside, what's the minimum x, what's the maximum x, right? Those are numbers. And then for each value of x, I'm determining what minimum and maximum y are. If I'm going the other way around, like this one up here, when I'm putting the y on the outside, then I had to say, okay, what's the minimum y I'm after, what's the maximum y I'm after? Those are numbers, okay? Once you establish those numbers, then you say for every y in between, what's the minimum x, what's the maximum x? And they might just be a number if the minimum is always the same. They might be a function if they're changing. Okay. So there you go. There is the changing the order of integration in an iterated integral.